And so our job today is to discuss the corresponding coordinate systems. So the agenda is for spherical coordinates. Let me give you an example of how that simplifies life. If you look at the equation for the sphere, x squared plus y squared plus z squared equals, for example, 1, so unit sphere in Cartesian coordinates. If we start describing dynamics on that sphere, then we would want to know the coordinates individually. So, for example, solving for x in this case, we're going to have 1 minus y squared minus z squared. Square root is a plus minus. Now, you can imagine if we start doing differential equations with respect to something like this. Well, firstly, differentiating this is going to be messy, right? So what's going to turn up in the denominator? Various things will turn up in the numerator, but also the solution isn't single valued. You would have to take a look at the positive and the negative leaf, and then making sure that they connect somehow. So you can see even before we start looking at Cartesian description of a spherical symmetric object, you can see we're in for quite a messy description. On the other hand, you all remember that the equation for a sphere, the equivalent equation is to say that, well, these are points that are equidistant from the origin, right, at distance 1. And so this already looks considerably simpler. And so we will now explore first the planar polar coordinates for rotationally symmetric systems in plane, then cylindrical for systems that are rotationally symmetric around axis, and then spherical for the systems with spherical symmetry. And it is the latter that are used an awful lot in quantum mechanics, because Coulomb force is spherically symmetric, and therefore a lot of atomic orbitals, for example, transform by the spherical symmetry group. In fact, all of your SPDF and so on orbitals, you don't know it yet, but they're actually eigenfunctions of spherical symmetry and can be derived from spherical symmetry considerations alone. Okay, so item 2 on the agenda is definitions. And what you will find if you go through Wikipedia, if you go through literature, if you go through common programming languages, is unfortunately a great deal of confusion, because historically physicists and engineers have had different conventions, mathematicians have invented something of their own. So our definitions here are ISO 3111, so the standard that has been designed to more or less fit everybody, and that is the standard that EUPAC recommends for chemistry and the one that we will be sticking to. Be careful if you are looking at, for example, aerospace engineering. They are quite used to something else, right? So their OPGO are something very different to our spherical angles. Okay, so the first thing we will consider is a plane. So if we have our y and our x, what would be a natural way to describe something that is given instead as the distance from the origin? So we will have a point, and that will be the distance from the origin. And then we will define an angle phi. And notice that the positive direction for a rotation is always counterclockwise. Right? I mean, which way the clock goes was decided by somebody presumably in the ancient Greece, and we are stuck with that definition. Likewise, the positive rotation has been decided at some point, I suspect at the dawn of modern engineering somewhere in the 18th century. So positive rotation is counterclockwise. Remember that well. So let us now go through the definition of what that is. So let's consider, for example, we've got a triangle here, and we can see a projection here, and x is plainly r cosine phi here. And y is phi sine phi, and these are called polar coordinates. We can do the inverse transformation as well. You remember again from basic trigonometry that r squared here is x squared plus y squared. So r is root x squared plus y squared. Strictly positive because the distance from the origin is always positive. Practically speaking, define it that way, right? If we want a negative direction, it's still a positive radius vector, but just a different angle. So in this case, r is greater or equal than 0. And then phi is a bit more complicated, so we can take a look at what a cosine phi, for example, is going to be. We know from here. So phi will be arc cos of x over r. This definition suffices for mathematics, but actually in computer science you will discover we are using a slightly different definition for phi. It is formally equivalent, but it's an arctangent. So the tangent of phi in this case is y over x, and therefore phi is an arctan y over x. I will not go into the details of why that is. This is to do with sign instabilities in the arc cosine type description. It turns out, if you're doing computer science, the so-called four-quadrant arctan can be implemented in a way that is numerically stable. And arc cos has difficulties. So for your calculations, when you're doing them analytically, you're fine with the arc cos. For the situations when you've got numerical calculations, it is better to stick with the arctan. Okay, so these are the polar coordinates. Imagine now that we take our system into the third dimension, but we retain the axis of rotation. So the system is cylindrically symmetric. We just have a height. And in that case, it's useful to have a hybrid coordinate system where we are polar with respect to the x and y, but we retain one Cartesian coordinate. So in 3 dimensions, if we draw our Cartesian plane, then we are going to have our unit circle still here, and we are still going to have our radius vector in the xy plane. So that's x, that's y, and that is z. So we will have our vector, and it will have a radius r, and it will have an angle phi. However, in order to move in the z direction, we will simply vertically raise our point, and it's going to be here somewhere at a height h relative to the xy plane. And so this way we do have a hybrid coordinate system that retains the useful properties of polar coordinates for rotational symmetry, but also has a height as the third parameter. And of course we will retain the x and the y as the definition, so we will have x equals r cos phi, y equals r sin phi, and z will be simply equal to h, extension in the third dimension. And so the reverse is again simply inherited from our polar coordinates. So h is z, then r is root x squared plus y squared, and our angle phi is the arctan of y over x. Okay, so this is for cylindrically symmetric systems. Imagine now that our system is a genuine sphere, or something like rotational diffusion of a molecule. Molecule rotates in solution because things are bumping into it. Then we need to update this coordinate system to adapt to the full spherical symmetry. So let's take a closer look at that coordinate system, and let's actually design that coordinate system. So let's say this is our x, this is our y, and this is our z direction. So how would we proceed to design a coordinate system on a sphere? Of course, I do know the answer already, right, because it's an ISO standard, but let's think about it. So we have a point somewhere here in 3 dimensions, and of course we do need the radius vector for it, so that is going to be here, and that is going to be our r. Then, we normally, in physics, like for example in magnetic resonance, various things begin at the z-axis, right? So things are oriented, for example, by that like magnetic field. And so we will define an angle here called theta, and we will define our first spherical angle as an angle with respect to z. But then we would like also, to some extent, to stick to this convenient notations that we have already developed here. And so the next step will be to project this into the xy plane. So to put it here somewhere, and that is our projection. And then it will have another angle, and we will simply inherit the angle phi. So there will be an angle here, that is fine. And now let's do the basic trigonometry to get ourselves z expressions for this. Okay, so let us begin with the z. Let's think about it. If this is our r, so the length of that is r, then the projection on the z-axis is going to be r cosine theta, right? Then the angle that this vector makes with the xy plane is the reciprocal of theta. So the amount that ends up in the xy plane is therefore the sine. So if we look at the y, that will firstly be r sine theta, but then we have the angle phi in the xy plane, and y is the sine part of it. So we have sine phi. And therefore x is r sine theta, right? So projection into the xy plane, and then projection onto the z-axis, so that's cos phi. Okay, nice. So these are the isospherical coordinates. And that is the graph. So solving it backwards is, of course, non-trivial, but you have to do it once in your life, so let us do that. So for this, maybe I should draw it here. Let's think about what is r. Well, it's just basic Euclidean geometry. So r squared is x squared plus y squared plus z squared. And so this is the root, again positive by definition, because if we want the opposite direction, we can keep r positive, we can simply adjust the angles. And then let's think about theta. So we know that we have this relationship, so cos z and r. So the easiest thing to do is r cos of z divided by r, so root x squared plus y squared plus z squared, so strictly Cartesian expression on the right-hand side. Now for the phi, imagine we take this and divide it by that. Then r sine would cancel and we would have a tangent here. And so we can use the arctangent, same as that. So we have phi, will be arc tan y over x. And those are the reverse relations for the spherical coordinates. So let us now go and do a few things with them. Let us, for example, demonstrate this fact that I have alluded to at the very start of the lecture, that the equation for a unit sphere becomes particularly simple. So our x squared plus y squared plus z squared. Let us substitute the definition of spherical coordinates and demonstrate that that is indeed the equation. So x squared r sine squared theta cosine squared phi plus y squared r squared sine squared theta. Sine squared phi plus z squared, that's r squared cosine squared theta. Okay. So here, let us take r sine squared out of the brackets. So this is the square of course r squared sine squared theta, and then cosine squared phi plus sine squared phi materializes in the bracket, and that is of course equal to 1 plus r squared cosine squared theta. Okay, so we are left with r squared cosine and sine. Take r squared out of the bracket, so cosine squared theta plus sine squared theta. That is again 1, and that is simply r squared as expected. And if this was equal to 1 originally, then that is equal to 1, and so that is our simple expression for the sphere. And similar things happen to functions of Cartesian coordinates that naturally have spherical symmetry. The expressions for them simplify quite a lot. So let me give you another example. If we look at the logarithmic spiral, the expression in spherical coordinates, well in this case polar, is quite simple. If we look at it, it's r, and it's a function of phi, and this is a e to the power b phi, where a is the initial radius of the spiral, and then b, if b is negative, the spiral will fade in as it goes. So if we plot it on a Cartesian plane, so x, y, still the plot is Cartesian. Let's think about what it's going to have. So at phi equals 0, we would have the exponential that is equal to 1, and r is equal to a. As per the definition of our polar coordinates here, phi 0 and r equal to a is sitting on the x-axis. So this is a. As we start increasing phi, the radius vector is rotating, but for negative b it becomes shorter. And so what is going to happen is we will have a spiral that just goes into the origin eventually, right, after a few revolutions, depending on the magnitude of the particle. Let us, however, now try to obtain the Cartesian expression for this. You can kind of see that we are in trouble already, because in Cartesian coordinates this function isn't single valued. And in fact, in certain situations it may have countably infinitely many values for every value of x. So let us go and express that in Cartesians. Okay, so we have on the left-hand side here, we have r, which is root x squared plus y squared plus z squared, which is equal to a, and then the exponential of b, and remember what was phi? The phi was arc tangent y over x. Over x, well, we can try and simplify this. We can take logarithm of both sides, in which case the power half will pop out in front. So we can say 1 half log x squared plus y squared plus z squared equal, we can split the log here and take the b out. That will be log a plus b log of r tangent of y over x. Further simplifications are possible here. Log of reciprocal trigonometric functions can be simplified if you try really hard. But you can imagine that if I gave you in the examination an equation like that, that would have been cruel and unusual, right? Nobody would have been able to plot, except by calculator, and probably not even then, the graph of that. However, if I do give you the function like that, and I explain you the polar coordinates, you would have no difficulty plotting the graph. It's just the standard spiral in the xy plane. Okay, so that is an illustration. Let us now also, because we will be dealing with differential equations, go through the transformation of derivatives. Because now that we've got some differential equations in Cartesian coordinates, we need a way of translating them into polar and spherical. And for that, I will remind you the multivariate chain rule. If we have a function, so f of x of alpha, and let's say also of beta, so beta and then of y, of alpha and beta. So we have a function that depends on multiple coordinates, which are themselves dependent on multiple other coordinates. So you've had that in the previous semester, and I will just remind you that df by d alpha in this case is df by x by d alpha plus df by dy by d alpha. The generalization of the chain rule for functions of multiple variables that depend on multiple other variables. Okay, so let us go and do the corresponding transformations using the coordinate systems that we have just defined. So let's say, for example, that we want df by dr. Somewhere here, I suppose. So df by dr, and the example says that we are working with polar coordinates here, and f is x squared minus y squared. And we want the derivative with respect to the radius vector. So this, as you can probably plainly tell by now, is a saddle. Right? It's a quadratic function with respect to x, positive, and a quadratic function with respect to y, negative. So in the two-dimensional plane, you will have a saddle function, and it's not entirely obvious what the slope of a saddle is with respect to the radial direction, right, in different angles. So let us do that. So what we need to do is to just literally apply that rule. So df by dr is going to be df by dx, dx by dr plus df by dy, dy by dr. Okay, and here we actually know all of the derivatives. Df by dx is just 2x. So that is 2x. dx by dr is cosine phi. And plus df by dy, that's minus 2y. Y. And dy by dr is sine phi. But we are told to obtain the answer purely in polar coordinates. So of course we need now to transform the x and the y as well. So our x is r cosine phi. So we have 2r cosine squared phi. And then we have minus 2y, and so y is r sine phi. And so we have 2r sine squared phi. And we can do some arithmetic simplification. This is r, and then cosine squared minus sine squared is cosine 2 phi. And that is the slope. So you can see the slope increases with the radius vector, as you would imagine for a biquadratic saddle, but it's also a non-trivial function of direction. right? The slope is clearly positive in some directions and negative in some directions, as you would expect for a graph like that. Okay, so this is the basic transformations and the definitions, and now we move to the topic where all of this infrastructure is being used in practice in chemistry, and that is the spherical Laplacian. So next item on the agenda, spherical Laplacian. Let me remind you something from quantum mechanics about the energy of an electron in a hydrogen atom. So remember what the energy was. It had the momentum part and the potential energy part. And if we are talking, if we've pinned the nucleus, just nailed it to vacuum, and we've got the electron around it, then the energy of that electron is going to have the momentum part, so that was mv squared over 2, and it would have the potential part, and that would be the Coulomb interaction. So E squared, so if we are looking at a hydrogen atom, over 4 pi epsilon naught R is the energy of the Coulomb interaction in this case. So remember, charge squared over the 4 pi epsilon naught, and then 1 over R, that's the distance. You can clearly see that the energy, the potential, is spherically symmetric. However, this mv squared over 2 appears to be a Cartesian expression because it's got the velocity squared. And we should actually rewrite this. I will remind you that momentum is mv. And that is necessary in quantum mechanics because the so-called canonical coordinates in quantum mechanics are not coordinate and velocity, they are coordinate and momentum. The reasons are technical, I will not go into them, but we need to express this as a momentum. So we have E squared over 2m minus E squared over 4 pi epsilon naught R. And that's our energy. In order to obtain the corresponding quantum mechanical energy operator, the Hamiltonian, what we must do is we must replace every instance of the momentum operator. So for example, dx, the momentum in the x direction, becomes minus I h bar d by dx. So the momentum operator is a differential operator. And as you can see, it's a derivative with respect to a Cartesian coordinate. Then if we go and take a square of it, so dx squared, it's going to be minus d2 by dx squared with the h bar squared in front. And then if we take all three of them, we will have minus h bar squared, d2 by dx squared, d2 by dy squared, d2 by dz squared. So let us write that out. So the energy operator for this system is going to be minus h bar squared over 2m d2 by dx squared plus d2 by dy squared plus d2 by dz squared minus charge squared 4 pi epsilon naught r. Horrendous operator, right? We are looking at a second order partial differential equation, and when we write the corresponding eigenfunction relation, right, h psi equals e psi, these functions are known to you as atomic orbitals of the hydrogen-like atom. So all of these fancy shapes, bell-shaped, squiggly curves for d orbitals and so on, they come as solutions of this equation. However, we have a problem here in that part of it is Cartesian and part is spherical. If we start expressing this via Cartesians, this is root x squared plus y squared plus z squared. we cannot extract any individual coordinates. The moment we start differentiating it, things get messy. So a better way here would be to translate the derivatives into spherical coordinates, because it's kind of alright, right? We've just translated a few. Now this operator here has a name. It's encountered a lot in diffusion equation, in hydrodynamics, as you can see, in quantum mechanics, in electrodynamics, in Maxwell's equations, and so on. In fact, Pierre-Simon Laplace, I believe, encountered it in heat transport. Anyway, it's denoted delta, capital Greek delta, and it's called Laplacian. And these days, you can actually get Laplace's book. It's in French. And see for yourself how he derived it. Anyway, our mission today is not actually to do it. It's 5 boards of dense algebra, but to sketch a path of how we translate the Laplacian into spherical coordinates, and then to discuss a little bit the final answer in terms of the atomic orbitals that you have already seen. So let's make a start. So let's say we want to take a derivative operator, d by dx, and to translate it into spherical coordinates. What do we need to do? Well, that is going to be, so of course we have a function that is implied here, but we will not put that function because I want you to train your hand and your eye at manipulating abstract operators. We will use this generalized chain rule. So if we have df by dx, that is df by dr, dr by dx, df by d theta by dx, df by d phi by dx. But operator notation requires us to have the operator last. I mean, otherwise it can act on its own multiplier, and that would not be correct here. So what we have here is therefore, so we need d by dr. So we have dr by dx, and no, wait a minute. So we have df by dr, dr by dx. So that is our operator that will differentiate our function, and that is a multiplier. So in order to not overcomplicate the notation, we put dr by dx here, and then this is our, what used to be df by dr, but it is d by dr. Right? So the function in front is implied. And likewise, we do that for the theta and the phi. So d theta by dx times d by d theta plus d phi by dx d by d phi. Okay, so this is the expression for this derivative, but now in spherical coordinates. So we would need to take our function, differentiate with respect to r and multiply by this, differentiate with respect to theta and multiply by this, differentiate with respect to phi and multiply by that. And these derivatives we actually know because we do know the reverse relations here of r, theta, and phi. But as you can see, they are, well, quite messy because we have inverse trigonometric functions. So we need to massage them a little bit to make them easier to differentiate. So what I'll do is I will rewrite r as it had been. So r is root x squared plus y squared plus z squared. Nothing we can do there. But I will return the cos onto theta. So I would say that's a cos theta, and that is our z over r. And likewise tan, so it will be sine phi over cos phi, that is equal to y over x. And this way it's a bit easier to differentiate, as you see. Okay, so let us get ourselves dr by dx. dr by dx is going to be, well, 1 over 2 roots, and then the derivative of whatever occurs under this. So 1 over 2 root times the derivative of x squared with respect to x, so times 2x. Root is r over there, so we have x over r, and that is so far so good, quite straightforward. And we would need to express x via r and the two angles. And so x is sine theta cosine phi. So you would have r sine theta cos phi over r. And so that is sine theta cos phi. Okay, not too bad. Now dr by, well, d theta by dx is going to be, we've got it as a cos, so let us differentiate both sides of this with respect to x. So we will not immediately do that. We will take d by dx of cosine theta equals d by dx of z over r. Cosine theta is easy to differentiate, so we would have minus sine theta times d theta by dx, which is what we are looking for. And then on the other side, we differentiate this. Z does not depend on x, but r does. So we would have the quotient rule in here. So the numerator prime is 0, then minus denominator prime. So minus dr by dx over the denominator squared, r squared. Dr by dx we have already obtained, so that is minus sine theta cos phi over r squared. Okay, and now we cancel sine theta on either side, cancel the minus as well, and we obtain d theta by dx is going to be cosine phi over r squared. As you can see, again, not too bad. Finally, we need d phi by dx, and once again we will differentiate both sides of that expression and then solve it eventually for d phi by dx. Okay, so d by dx of sine phi over cosine phi is d by dx of y over x. On that side, quotient rule, so we have sine prime, that's a cos phi, and then d phi by dx, times the denominator, so that becomes cosine squared, minus the derivative of the denominator, so that is a sine, so we have sine phi, and then d phi by dx, times the numerator, so that is a sine squared. That's nice because things get simplified, over cosine squared of phi. That's the left-hand side. On the right-hand side, y doesn't depend on x, and so that's simply minus y over x squared. Okay. Cosine and sine give us 1. Cosine squared we will move over there. So we have d phi by dx, and that is equal to minus y over x squared cosine squared phi. And finally, we need to substitute the actual y and the actual x. So in spherical coordinates, y is r sine theta phi over r squared sine squared theta cosine squared phi, cosine squared phi. Cos and cos cancel. Sine cancels one unit of it with the sign in the denominator. 1 over r remains, minus remains, so we have 1 over r. And then the sine theta in the denominator. And I think it's the sine phi in the numerator, that's right. Okay, and that's d phi by dx. So what we've done here is we have fully completed the transformation of our d by dx. So let us write that out explicitly. d by dx is now going to be dr by dx, so sine theta cos phi times d by dr plus, is that a plus? No, that's a minus. So, oh no, it's a plus. So plus cosine phi over r squared d by d theta. And finally d phi by dx, that is an actual minus, minus sine phi over r sine theta d by d phi. And that's it. So if we want to take a spherical function and we want to differentiate it with respect to a Cartesian variable x, that's how we do it. Now, as you can imagine, we would have to do exactly the same for d by dy, and then for d by dz, and then we would have to take squares of them, and so of course, if you square this operator, it acts on itself, and then it's a giant pile of product and ratio rules, because not only the derivatives are going to be transformed, they're actually going to be acting on all of these pre-multipliers as well. And so a giant pile of mathematical transformations then results in two parts for this Laplacian. So let me make some space in here. Just write that down and discuss it a little bit. So what you have there is this delta that is our notation for the Laplacian. It has a well isolated radial part, d2 by dr squared plus 2 over r d by dr minus 1 over r squared L squared. So this L squared is a purely angular operator. So L squared is d2 by d theta squared plus cos theta over sine theta d by d theta and plus 1 over sine squared theta d2 by d phi squared. Okay, so this could just about have been done by Schrödinger when he proposed Schrödinger's equation for the hydrogen atom. However, Schrödinger himself couldn't solve it. And you can plainly see why. It was Eugen Wigner that solved it for him. And the eigenfunctions of this operator are called spherical harmonics, and these are your atomic orbitals that you see in the textbooks. L is your orbital quantum number and M is the magnetic quantum number. Now then, once you've got those, you can add the radial part. This is what's called Laguerre's equation, and the solutions are Laguerre's polynomials. And then when you plug the corresponding function there and do all of the mathematics with the condition to decay to 0 at infinity, you get the radial parts, rho of r, and they're enumerated by n, the principal quantum number. So this part of the equation is responsible for your energy levels in the hydrogen atom, and that part is responsible for the orbital and magnetic quantum numbers. Schrödinger equation does not explicitly consider spin. Spin comes from special relativity and is introduced into the equations that you have post factum, somewhat artificially. Okay, so in this course we will not go through the full complete solution of this core. This is 3 separate lectures, so you can see them online. Actually, previous iterations of this course did have that solution, but then we replaced them by Chris Scalaris' numerics. So we take the expression for the energy, we write the corresponding differential operators. As you can see, translating them into spherical coordinates is super painful. And then solving that in spherical coordinates is also super painful, but less super painful than having had to do that in Cartesians. At least, you know, the variables here are separated into radial and angular, whereas we would not have been able to separate anything out if we were with it in Cartesians. Okay, the summary of the lecture. There are 3 fancy coordinate systems whose definitions I am afraid you will need to memorize. You will need to remember that. The easiest way to do it is exactly the way I've just done it, by just drawing a schematic, which is easy to remember, and then use basic trigonometry to work out the expressions. You will not necessarily have to manipulate the coordinates themselves as much as you would have to manipulate functions of those coordinates. So you need to be able to translate things between Cartesian and these. And more importantly, we expect you to be able to translate at least first derivatives. Right? So second derivatives are a disaster, but first derivatives using these multivariable chain rules, you should be comfortable with, and you will have plenty of practice in your workshops. Any questions?